Alright, welcome back to my YouTube channel. So today we'll be solving a very simple problem on the perturbation theory. So we are going to apply the perturbation theory method and also the exact effective frequency. So let's dive in deeply. These are questions we were given. I was asked to calculate the first order correction energy, where we were given a very small a small perturbation of the form. So first of all, our first order correction energy, mind you, we are starting with the perturbation method. So it's given by this, where this is a perturbed Hamiltonian that we were given for these questions. We also need to note that our Hamiltonian of the harmonic oscillator is giving us H0, which is this, and this also is our eigenfunction. So might not be using this eigenfunction for expression in this context, because we want to avoid using so many integrals. So going back to our first order correction, if we substitute our Hamiltonian, we are going to have this expression here, and the next thing is to evaluate this matrix. And we can evaluate this matrix when we employ the ladder operators. It's easier to solve it that way. And these are ladder operator we are going to employ. X is giving us this expression, and this is our lowering operator. This is our raising operator. So if we look for x squared, we are going to end up with these expressions. And mind you, this expression and this expression are different, but actually the same. The presentation is a little bit different, and we got it by again using the canonical transformation. So this is canonical transformation we used, and if we just make this sublet of the formula and substitute it, we're going to end up having this entire expression. So the next thing we need to do is to substitute this entire expression for x squared into this matrix. And we can do that by saying this. Now if you notice, we can pull out this constant from here, and it's out here already. So the next thing we need to do is to evaluate this matrix again. Of course, that can be given as this, because we can just simply expand the brackets so that this ket and this bra acts on each of these operators here, and also here. So we are going to have this expression. Now what we need to do next is we have to solve for each and every of these expressions here, and we can do that by simply applying letting this operator to act on these kets each places. Now if we do that and applying our Dirac chronicle delta principle, we're going to have this expression again. So we're going to have this, and of course, since n and n minus 2 is not the same, we are going to have 0. We are going to vanish. So this is going to be 0. This is also going to be 0, and this is going to be 1. Don't forget, we have our chronicle delta formula giving us direct delta function of n to be equal to 1 when m is equals to n, and 0 when so it's not equal to n. It's not equal to n. So if we move on, we are going to finally have our first order correction energy to be given as this. So this is our first order correction energy. So diving deeply to our second order correction energy, we have our formula given as this, a little bit complex but very easy. So this is our second order correction energy, and what we need to do is that we need to evaluate this matrix, we need to evaluate this, we need to evaluate what this is. And we can do that simply by, first of all, bringing back what was x squared. If we put back what was x squared, we are going to have this expression. Now we are going to evaluate this expression again for this state, which is this bra here and this ket. So we're going to expand this again. To expand this, we first of all look at this. We removed the bra, so that this operator acts on the ket first of all. So you see the step we jumped before, I'm expanding it here now. So if this operator acts on this ket, we are going to have this entire expression here. This is a basic quantum mechanics playing with bra and the ket notation, lowering operator and the raising operator. So we are going to have this entire expression spelled out this way. Now if we bring in our bra to act from the other end, so we are going to have this, and we can expand and treat this by using the inner product. If we use the inner product, this is going to give us this. So you see, we've gotten our Dirac, chronicle Dirac here again. Chronicle delta, please. Our chronicle delta is everywhere there. Now, here we are going to have this expression, this. So you notice that j and n minus 2 and j and n plus 2 is the only part that is left that will not be 0. So when j is equal to n minus 2, we are now going to have this, because this is now going to be 1. And when j is equal to n plus 2, we are going to have this one again as 1, and this one will become 0. So which is finally, we can put it back. First of all, our unperturbed energy is giving us this, and we need to also find En naught minus Ej naught. And first of all, we'll start with when j is this is for j equal to n minus 2. When j is equals to n minus 2, we are going to have En naught minus Ej naught to be, so this is our E naught, this is our Ej, n is equals to j is equals to n minus 2. So we are going to finally have 2 h cat omega. If we do same thing here, we are going to have negative 2 h cat omega. So we can substitute finally. When we substitute finally, we are going to have this. We have made use of the substitution. So the substitution is carrying when j is equals to n minus 2 plus when j is equal to n. So that's what the summation is going to be. So if we expand the summation very well, we are going to have this as our final answer. Moving on. So our method 2, we are going to absorb the perturbation directly into the unperturbed Hamiltonian of the harmonic oscillator, and we are going to find the exact energy levels and then expand them for small perturbations, more like the Taylor series. So we are going to have this. So this is h naught plus h prime. So if you notice here, we are going to add our perturbation here and absorb it there. So we are going to have something like this. So we can just let k prime to be equal to this. So you see, I made every expression here to just be equal to k prime. So if you make that, also you can also have omega prime to be the square root. Don't forget, omega is equals to square root of k over m. So omega prime should be equals to square root of k prime over m. So that is simply what I did. So if I expand for omega, if I bring omega out, I'm going to have this expression here. So our eigenfunction will become this. So there's a lot of algebra that I've skipped to get our eigenfunction En to be this for this particular method. So if this is our eigenfunction, expand this for small perturbation and use the binomial approximation. So 1 plus x raised to the power 1 over 2 is approximately 1 plus 1 over 2x minus 1 all over 8x squared, of which we can finally do same thing for this expansion, because we have we also have 1 over 2 here, so we can do this same expansion here, and we are still just going to replace x with this function and x squared with this. So if we do that, we can expand these brackets and have our first term to be the unperturbed energy, the second term to become the first order correction energy, and the third term there to become the second order correction energy, which is same when we solved it from the perturbation theory. All right, thank you very much, and see you on in our next class.